Hi guys, I hope you still have some energy left for the last talk of today. I'm Rashmi, I'm an engineer with the platform team at Twitter, and I'm here to talk about using Redis at scale at Twitter. And to do that, I want to talk about Nighthawk. To set up the agenda for today's talk, this is what I'll be covering, right? What is Nighthawk? How does it work? How do we scale out with Nighthawk? How do we achieve high availability with Nighthawk? And finally, I want to talk about a couple of distributed caching problems that we're trying to tackle at Twitter today. So what is Nighthawk? Nighthawk is a distributed caching solution that runs Redis at its core. Any service that needs a Nighthawk cache gets its own Nighthawk cluster. So at any given point in time, we're like running a bunch of Nighthawk clusters. To give you an idea of the scale at which we run Nighthawk and Redis, I'd like to share some numbers. One of our larger Nighthawk clusters has been scaled to serve more than 10 million queries per second. Our largest Nighthawk cluster, in terms of number of Redis instances, runs 3,000 Redis instances at any given time. Another of our larger Nighthawk clusters has been scaled to store more than 10 terabytes of data. The reason we can do this is because Nighthawk is both horizontally and vertically scalable. So let's see who uses Nighthawk at Twitter. Some of our biggest and important customers are as follows. We have Twitter Analytics, which provides ad and video engagement information. Then we have ad serving. This is the service that is directly responsible for Twitter's revenue stream. It basically matches ads to users, scores them, and finally serves the ads to users at an immense scale. Then we have Ad Exchange. This is Twitter's real-time bidding platform for ad targeting. Then we have direct messaging. This is a more user-facing feature of Twitter service. I'm sure most of you must have used it at some point in time. And finally, we have mobile app conversion tracking service. This is a service that basically tracks conversion of promoted app installs. Conversion would mean something like, did a user install a promoted mobile app? Did he engage with the app, such as logging in or signing up for a service? So what was the thinking when Nighthawk was designed? It was designed to achieve some goals. The first thing is it should be scalable. Nighthawk with Redis should be horizontally and vertically scalable to adapt to a dynamically changing caching needs. Secondly, it has to be elastic. We should be able to add instances or remove instances from a cluster without causing any service downtime, without overwhelming the downstream storage, and without impacting the upstream client. Then, of course, we needed high throughput and low latencies. This is pretty straightforward, so I'm not going to say anything more. Then we also wanted to achieve high availability in the event of machine failures, which means that even if we lost a machine or an entire rack, we still have your data to serve the client. And finally, we wanted to have a topology-agnostic client. There are some benefits to separating out topology management and partitioning management outside of the client, and its advantages are going to get more clearer as I talk about it in the next few slides. So this is what Nighthawk looks like. It has three main working components. One is the backend layer. You can have one or more backend instances, obviously. Every backend runs one or more Redis instances. Then we have the proxy and the routing layer. This is a stateless layer whose main function is to forward the incoming client request to the appropriate Redis node. The proxy layer also subscribes to topology changes, so it always has an up-to-date view of which partition is mapped to which Redis node. And then we have the cluster manager. The cluster manager is like the main orchestrator of the cluster. It is responsible for managing cluster memberships, and also it's responsible for balancing partitions and the replicas across the Redis nodes. In her Nighthawk cluster, the number of partitions are configured during cluster creation, and then it remains the same throughout the cluster's lifetime. The topology has information such as how many partitions are there in this particular cluster, how many replicas per partition, how many nodes, Redis nodes, that are participating in the cluster, as well as information such as which partitions are mapped to which Redis nodes. I'd like to delve a little more into the cache backend. Every Nighthawk cache backend runs inside a Mesos container. It has three main working components. Obviously, we have one or more Redis nodes running inside the container. Then we have a topology watcher and announcing component. Now, this is the component that subscribes to topology changes and reacts to it. And it is also responsible for announcing to the topology information about the locally running Redis instances so that they can be discovered. And then we have the node manager. This is the one in the green, actually. This is a lightweight piece of native code that basically is responsible for routing the incoming request to the appropriate locally running Redis instances. So when a backend instance comes up, the first thing that it does is it announces itself to the topology. Here we have three Redis nodes, so it announces information that Redis 1, 2, and 3 are running on this particular backend, and it can be found in this particular data center, a particular host, and it's listening on a certain port, as well as its capacity information. Now the cluster manager is going to see this topology change that 3 new Redis nodes have joined the cluster. And the next thing it does is, hey, these nodes are underloaded, so it's going to end up balancing some partitions from overloaded Redis nodes to these underloaded Redis nodes. So when it makes that new remapping and commits to the topology, the backend gets this information as well. Now the backend is aware that replica 1, 2, and 3 now reside on its local Redis nodes. And when this information reaches the proxy layer, it now knows that all requests to keys belonging to replicas 1, 2, and 3 now have to be forwarded to this particular backend. Let's next talk about Cluster Manager. Like I mentioned before, Cluster Manager is like the main orchestrator of the cluster. It is responsible for managing all the participants of the topology, such as the Redis nodes, the partitions, and the replicas, and mapping partitions to Redis nodes. In general, Cluster Manager is responsible for maintaining the sanity of the cluster and of the team. So one of the important things that it does is it's responsible for balancing and rebalancing replicas across the Redis nodes. Anytime a new Redis node joins or leaves, it is responsible to make sure that the replicas are distributed to the Redis nodes in proportion to the capacity of the Redis nodes. The other thing that it does is it reacts to topology changes. Say, for example, if a machine failed, the corresponding Redis node on that machine fails too. The next thing that it does is marks this Redis node as dead and moves any partitions assigned to it from the dead node to any available replacement node, if it's available, or to the other available Redis nodes. And in the case of replicated caching, it ensures that 2 replicas of the same partition never end up on the same failure domain. This means that if you lose a machine or an entire rack, it still has a copy of the data to serve. I want to talk a little bit about Redis databases for partitions, how we use Redis DBs to store data of our partitions. In our Nighthawk cluster, every partition is not just associated with a Redis, but to a specific Redis database. In this example that we have here, partition X and partition Y are associated, or I can say mapped to the same Redis node here. What this means is that partition X is associated with a unique Redis DB. In this case, it is Redis DB1. and then partition Y is associated with Redis DB2. So if keys K1 and K2 belong to partition X, they can be found in Redis database 1. And keys K3 and K4 that belong to partition Y can be found in Redis DB2. Now, there are some advantages to using this sort of a mapping. One of them is the unit of key remapping is much more granular. It's predictable. The number of keys that get remapped when you resize a cluster or whenever there is a topology change is no longer a function of the size of the cluster. You know that every time a partition remaps, it's basically the keys in that particular Redis database associated with it. Another advantage of this is that you automatically get logical data isolation. If there are a number of keys belonging to different partitions in the same Redis node, you can still uniquely identify and act on all the keys belonging to a particular partition. Say, for example, you want to enumerate all the keys belonging to a certain partition. It is as simple as figuring out what is the Redis and the database associated with that partition, which you can find out from the topology, and then calling a Redis DB scan on it. The other thing is, say, if a client comes and tells you that we see that keys and the values belonging to a certain partition seem to be corrupted, can you flush that data for us? How would you do it if you were storing data in Memcache, or even if you stored all your data but just in a single database in Redis? You'd end up flushing all the data, and the healthier partitions data is also gone. But in our case, what we can do is, if we know the partition to clear out, we can find out the corresponding Redis database and call a flush DB on it. This also enables some interesting new workflows. In the case of replicated caching, every partition has 2 replicas, if we use a replication factor of 2, right? So say if one of the replicas went down and came back up, now the restarted replica is empty. It has no data. This sort of a mapping allows us to find out the corresponding healthy replica, read all its data, and write it into the warming replica and bring it up to speed. I'll talk a little more about it in the next few slides. Let's talk about scaling. Say it is NFL season, and there's a lot of chatter happening on Twitter, which means that there are a lot more requests coming to the Twitter services and a lot more requests coming to the underlying cache. To understanding how we do scaling with Nighthawk, let's first see what scaling looks like with our regular client or proxy-managed partitioning scheme. In our example, we have a client talking to a cluster with 3 Redis nodes. And let's assume we have 1.5 million keys. A good partitioning scheme will try to distribute the keys across the Redis nodes uniformly. Let's take the ideal case, and we have about 500,000 keys per Redis node. Now a client comes and tells us, hey, we're going to increase the QPS to your cache by about 2 million. Go figure. So we go run the numbers and figure that maybe we're going to add a couple of more Redis nodes. And now you can see that the rightmost Redis node is double the capacity of the rest of them. A naive client partitioning scheme would totally ignore the fact that one of them has a higher capacity, but instead simply redistributes the keys uniformly across all these Redis nodes. In our case, the client instantly remaps 600,000 keys to these 2 new Redis nodes. As new requests come in, there are going to be a bunch of cache misses, and ultimately the requests hit the persistent storage. As more requests come in, obviously more cache misses, and very soon your persistent storage is seeing a request storm. And guess how the storage is feeling? Not very good at all, and so does the storage team. If there are a good amount of checks and balances in place, the persistent storage would end up rate limiting the client's request, in which case the clients are going to see a bunch of errors. In the worst case, storage is going to end up serving your requests with very high latencies, in which case the clients are going to just time out. In either case, the client's success rate suffers. Now let's look at what scaling out looks like Nighthawk and Cluster Manager. Here we have a Nighthawk cluster with a proxy layer. Then there are 3 Redis nodes in the backend. We have the topology and the cluster manager on the side. Let's consider the same 1.5 million keys. And since we know that in Nighthawk, the partitions are pre-created, let's assume for simplicity, we have 100 partitions, which means that we have 15,000 keys per partition. Now the client comes and tells us, hey, we're going to increase the QPS to your cache by 1 million, go figure. We run our numbers and find out that the backends can handle it just fine, but we may need to increase our proxy instances. We may throw a couple of more proxy instances. Awesome. The cache runs fine, we can handle this additional QPS, all looks good. And then the client comes back and tells us the next day, hey, we're going to increase the QPS to your cache by another 1 million. Okay, we go run our numbers and figure out that the recently expanded proxy will work just fine, but we need to increase the number of Redis. So we add a couple of more Redis instances. Note that the rightmost Redis instance is double the size as the rest of the Redis nodes. Now, the cluster manager is going to notice this change. The 2 new Redis instances have joined the cluster. So what it's going to do next is move some of the partitions from the overloaded nodes to the underloaded nodes. But what we do in Nighthawk is move the partitions in a controlled, rate-limited manner. We generally move 1 partition every t minutes. You could do it every 1 hour, or you can say, I want to move 5 partitions every 2 hours. You can choose whatever configuration that would suit your use case. So in our case, the cluster manager moves 1 partition from an overloaded node to the underloaded node, which means that 15,000 keys have been remapped. Now the requests are going to hit this new Redis node, and inevitably there'll be cache misses for these 15,000 keys, and it's going to hit the persistent storage. And after the balancing interval, whichever it could be 5 minutes or maybe even an hour, the cluster manager is going to move another partition from an overloaded node to the underloaded node. And now again, there are going to be 15,000 cache misses for these keys, and the requests are going to hit the persistent storage. But note that the persistent storage only has to handle requests for these 15,000 keys versus 600,000 as we saw in the previous case. So guess how your storage is feeling? Much better, right? So this whole balancing process can take anywhere from a few hours to maybe even a few days, depending on your cluster size and how many nodes you added and the number of partitions. At the end of the whole balancing process, this is what the cluster would look like. You can see how the rightmost Redis node, which is double the capacity, is also hosting double the amount of data. Now that I've talked about scaling out with client-based partitioning and Nighthawk with Cluster Manager, I want to quickly go over the advantages of using our approach. First, you have a thin client. It does not have to be aware of your topology implementations. You could have any partitioning scheme today. You could totally change it tomorrow, and you do not have to rebuild and redeploy the client. Second, the client, the proxy, and the backends can all scale independently. Like the use case that I just showed, scaling out with Nighthawk and Cluster Manager, we increased the proxy layer first, and then only when required, we expanded the backends. You could also plug in your own intelligent custom load balancing scheme into the Cluster Manager without having to, again, rebuild and redeploy your client. And since the way the partitions get remapped is in our control, it is possible to scale out, scale up, or even scale back without any cluster downtime, without impacting the storage, and without impacting the success rate of the clients. So let's now talk about high availability. Nighthawk achieves high availability using replication. And why use replicated cache, right? A consider the case of a data analytics pipeline, which generally uses the Lambda architecture, where you have a real-time processing pipeline, and then you have a batch processing pipeline. The real-time processing pipeline acts on real-time data, does some processing and transformations on it, and finally stores the result in a fast data store. Now, Redis qualifies as a fast data store. But note that these real-time pipelines could be reading data from, like, say, 10 different services, applying transformations on them, and finally aggregating them into a single key value before storing it into the Redis. Now, let's say we lost a couple of Redis instances, or even one. We have literally lost millions of keys. Recomputing these keys on a cache miss is expensive, both in terms of time as well as resources. Such services are well served by a replicated cache. Nighthawk provides synchronous best effort replication. We need synchronous because both the replicas of a partition will be serving production traffic all the time. And if one of those replicas died down, the other replica has to instantly take over all the traffic. And we cannot really sustain a large amount of inconsistencies. In practice, we use a replication factor of 2, which means every partition has 2 copies. And we only do intra-data center. We do it within the same data center. We don't support cross-data center yet. Because it is best effort, we support only idempotent operations, such as get, put, count, and so on. This is to ensure that we don't end up introducing inconsistencies if, say, one of the operations failed for a copy and the client retries. We would end up adding inconsistencies if, say, we were supporting increment or decrement. So that is the trade-off. We don't support non-idempotent operations. Also, we ensure that copies of the same partition never land on the same host, nor on the same rack. This is again to ensure in the event of machine failure or even a rack failure, we don't lose your data. Also, if a certain replica of a partition dies and comes back up, it is empty. It doesn't yet have all the data as a healthy copy. But then, as of today, we don't actively do anything about this situation. As the writes come in, the warming replica slowly warms up, and finally will catch up to the serving replica. Now, this warming time can take anywhere from a few hours to a few days. So obviously, we don't have the right way of working yet, but we are trying to solve this problem, and I'm going to talk about it in the next section. Replicated Nighthawk pretty much looks like the architecture diagram that we looked at. It has a proxy in the routing layer. It has a topology. It has a cluster manager. But note that we have 2 different pools of backend. You have the pool A, and then you have the pool B. All partitions have a replica, corresponding replica in pool A, and also a replica in pool B. So these are the 2 copies of your data. All writes that come to a partition is sent to both copies of the partition. And any reads that might come in for a partition, the proxy just picks up one of the serving copies available. In our case, it picked up backend N. What would happen if, say, backend N failed and the corresponding Redis died? The cluster manager obviously is going to go and mark that this particular Redis node is dead in the topology. The proxy, which also noticed this topology change, will now look for another serving copy of partition 5, which is found in backend 0, and it'll reroute the request to the serving copy. Now say the backend N got replaced with backend N star. It's hosting the same set of partitions. Now that this Redis that just restarted is empty, all the replicas go into warming, indicating that it doesn't have all the data yet, but it is ready to serve the write requests. And as the write requests come in, the warming replica slowly gets populated organically and finally will catch up with the serving replica. In this section, I just want to talk about a couple of distributed caching problems that we face today at Twitter, and we're trying to solve as well. Remember this? This is Ellen's Oscar selfie that went super viral on Twitter. It garnered 3.4 million retweets and 2.4 million favorites. This was the most retweeted tweet of 2014. Yes, it got that title. This is a classic example of a hotkey. Imagine the amount of QPS hitting the cache server that was hosting Ellen's user information. Hotkeys are keys that are extremely popular. They have such abnormally high number of requests that they literally bring down the cache server. They generally manifest themselves in the form of, say, one cache server seeing super high CPU utilization. And if the keys and the values are large enough, they quickly saturate the network link of the server as well, which in turn results in packet drops, TCP retransmits, and ultimately the client's timeout. So how are we handling hotkeys? Before that, yeah. This is a graph that shows what a typical hotkey symptom would look like. You can see that the line in green, this was actually during a hotkey situation. The line in green shoots up. It's the QPS to a cache server, shoots up suddenly, and it's higher than the average QPS to the cache cluster, and it stays there for a non-trivial amount of time. So if you ever saw this in your metrics, that is clearly an indication of one popular key in there. So how do we handle hotkeys in Twitter? One of the things that we do on the server side, at least for identification, is we sample a very small percentage of our requests and log the keys, obviously, into a log. And whenever we see symptoms of hotkeys, such as abnormal high QPS or super high CPU utilization, we post-process these logs to identify which are the keys that have a very high frequency of occurrence. And then we can always go back to the client and say, hey, these are the keys that we think are potentially hotkeys. Can you go cache on your side? The other thing that we do, at least on the client side, is the clients themselves run these hotkey detection algorithms. What they do is basically check if there is a certain key that's queried at a rate that is at or above a certain threshold, they qualify as a hotkey, and they cache it themselves. But this is not foolproof. In practice, we have seen that plenty of times there are keys that get queried at a significantly high rate, but just below this threshold, and they escape detection. And when they are queried at that rate by thousands of clients, they quickly snowball into a hotkey on the cache server side. So the lesson we learned is that hotkey detection is best done on the cache server side and nowhere else in the client. So what would be awesome to have? It'll be great if Redis tracked hotkeys, right? And it'll be awesome if they provided the protocol support to send the information back to the client and tell it, hey, this key that you're querying is a hotkey, so go cache it. Another problem that we're trying to solve is the active warming of restarted replicas. So I just talked about how in replicated Nighthawk, every partition has two replicas. If one of the replicas went down and came back up, it is empty and goes into warming, indicating that it doesn't have all the data yet. Now, I mentioned how we rely on organic repopulation of data as writes come in and slowly the warming replica fills up. But this can take anywhere from a few hours to a few days for it to catch up with a healthier replica. This opens up a wide window of vulnerability wherein your serving copy could also go down. And if it did, you just lost a bunch of your data. It's a complete data loss. So what we're trying to solve is to reduce this window of vulnerability from a few days to a few hours, and from few hours to minutes. So we're thinking, maybe we should have something like a bootstrapper service, which can consult the topology to figure out which of the replicas inside the cluster are warming. And if there are any warming replicas, it can find out from the topology if there is a corresponding serving replica. And from the topology, you can find out which Redis and which Redis DB that particular healthy replica is associated with. And using Redis DB scan and other magic tricks, you can read the values and keys and write into the warming replica. Well, this all sounds great, right? But then, we cannot be too eager about copying the data from one Redis to the other. That's because note that the warming and the serving replicas are serving production traffic. So we cannot end up bombarding these cache servers with our copy requests or end up saturating the network link with our copy data. So it's very important that the bootstrapper does the copy in a rate-limited manner. We need rate limiting both at the request level and at the copy rate level. And also ensuring that we don't end up introducing inconsistencies in the two copies of the data. So now that I've talked about some of the problems that we are trying to solve at Twitter, I'd like to conclude the session and open up to any questions you may have. So as of today, we don't have any specific solution on the server side except for the diagnostics purposes. We do the logging. But the client services, they themselves have some sort of like basic algorithms to figure out if a certain key is being queried at a certain threshold rate or even above it, then they automatically cache it locally. So it's not like a precise detection, but at least it's better than bringing a cache server down on the other side. It's better to be safe, to more eagerly cache them.
Your topology configuration propagate to clients, the proxies, and do you ever run into problems propagating that configuration?
I would say the propagation is pretty instant. We store our topology in Zookeeper, so basically they're implementing some form of watching, Zookeeper Watcher. So I have not seen anything more than a few milliseconds delay from a topology change committed to Zookeeper and the other end receiving that change.
What do you guys do in case of a sustained latency issue for a Redis node?
Sustained latencies in a particular Redis node?
Yeah, during your partition rebalancing?
So we don't do partition rebalancing based on bad latencies. We do it more based on if actually the Redis server died, like the node went away.
Now, I think that my question is, during the constant rebalancing, there could be a potential of latency getting introduced when the request goes to that Redis node.
When the request goes to?
To that specific Redis node, which is going through the partition rebalancing?
Not really, because partition rebalancing is basically key remapping. It's just that the proxy is now going to redistribute the keys and say, instead of querying this particular Redis node for the set of keys, if it got rebalanced to this Redis node, it's going to start querying this Redis node for the same set of keys. Okay. So it's not really affecting in any way the latencies of the Redis node itself. Unless that you did a bad job of rebalancing and like one Redis node has like way more partitions, which means it's getting way more requests for all the data it now is supposed to host.
I'm relatively new to Redis, so my question might be a little naive. You said that when you move keys, let's say 15,000 keys from one cluster to one node to another node, there are lots of cache misses.
Yeah.
Do you just change the key mapping and move the actual data from?
No, we don't move the actual data. It's just a key remapping. Yeah. Moving the.
Can you repeat the question?
So his question was, when we do the partition remapping, is it just the key remapping, or do we actually move the data as well? So the answer to that is we don't move the data as well as of today, because one, we have to consider that when we have clients requiring like very few milliseconds of latency, bombarding it with this copy requests as well is going to shoot up the latencies really high. So in the case of, at least for non-replicated clusters, generally they are the services who have like much more higher requirements of low latencies. That's like a no-go. They'd rather have the cache miss, go to the persistent storage, and then refill the cache themselves.
You have a long history, I think, of using Memcache, but then also Redis. What sort of use cases did you move over to Redis, and do you have a goal of moving everything to Redis, or where do you draw the line there?
For most use cases that have very flat keys and values, and also obviously that don't require data structure support, they are well served by Memcache, so we don't really try to push them hard into moving into Redis. But there are many other use cases which need the data, especially we extensively use hash table. So such use cases are well served by Redis, and most of our clients who want replication are served by Nighthawk and Redis. As I explained in our, how Nighthawk works with replication and how we use Redis databases for partition, that enables us to build up interesting workflows such as, active rehydration of, warming replicas and all of that. That's very beneficial for, services that require replicated cache. We cannot really implement that with Memcache. So in that way, when you weigh them together, Redis comes up here, and Memcache is not super friendly for replication.
How do you decide how big to make your Redis clusters? How do you decide how many keys to actually even store in total?
In general, the number of keys to be stored is determined by the service. We really don't know. But what they'll tell us is, we think these are the number of keys, and probably will grow to this number of keys, but at some point it just, it's moot, because we are more driven by the QPS growth and the data growth. And in that case, initially, the service owners are going to come and tell us, we need a cache cluster for, say, 5 million QPS, we need replication or we don't need replication, and that we need to store a minimum of, like, say, 500 GB of data. And based on those numbers, we figure out, okay, how many Redis do we need? Should we have more thin backends, in the sense like smaller number of Redis per backends and scale it out wider? Or should we just have, say, for example, a memory-bound cluster, like more data but less QPS, is well served by a more scaled-up backend, like, say, bigger Redis or many more Redis instances per backend, but much more smaller in size.
Do you have a rule of thumb inside the company? Do you have a rule of thumb inside the company about how much data in the persistent store for that application versus what the size of the cache should be? Like 50% of the data should be in the cache, or 80%? Do you have rules of thumb about that?
No, it's totally based on the use case, because some folks are okay with, cache miss, I'll just go to the persistent storage. If, say, it is a QPS-bound cluster where they have a lot more queries per second, then they are, and if the persistent storage also cannot, provide the latency requirements and throughput requirements of the service, in the case of cache miss, then that is a case where they'll end up storing a lot more data in the cache compared to, say, persistent storage.
Great, thank you.
Yeah.
Have you ever had a customer come back and say, we want you to resize our partitions? Like, we started out 2 years ago and the partitions were this size, and now I want a different size. And if so, what did you do about it?
Luckily, we haven't had any customer come and ask us about resizing our partitions, but it is a problem we're actively thinking about today. Because as you scale and your cluster becomes big, the partitions are stretched too thin. In general, the rule of thumb that we follow is, even if you quadruple the cluster, we choose a partition count large enough that even if you quadruple your cluster, which is not going to happen at least for a few years, each node can at least have 5 to 10% of the load. So that's how we size it. Like, we're thinking ahead and then sizing for today. But to precisely answer your question, we don't have any customers coming in and asking for it, but we're actively thinking about it as we are growing our clusters as to how we can do that.
Have you looked at Redis Flash? Can you
say that again? Sorry.
Redis Flash.
Flash.
Have you looked at using Flash? And have you chosen to use it? If not, why not? What are the trade-offs associated with using a two-tier caching hierarchy?
We haven't evaluated that. Definitely not Redis Flash. Tiering is interesting to us. Perhaps maybe the storage team could consider it, but we're not actively thinking about having a Flash-based cache.
Is it because cost doesn't matter for these types of situations, or
no, nothing like that. I guess I wouldn't have the answer for that exactly.
In a replicated setup, my understanding from your presentation is that from your proxy layer, you write to all replicas. That's a synchronous write.
Yes.
Has that been a latency issue for you?
It definitely takes a small hit on latency, but it is negligible enough that the customer cares way more about availability than, say, a couple of milliseconds of increase. Are we done? All right. Yeah. Thank you so much.